Okay, so now we're at this dramatic moment. We just set up our first Markov jump linear quadratic problem, and we took what did we do? Pretty simple. We took.
Tom, just before you start, we did actually have a question here. Maybe Mum will just take that before we get going again. Is that okay?
Okay, so what did we do? We took a standard, something we knew how to do. This is how progress is always made. We took something we knew how to do, and we changed it a little bit by combining it with something else we knew how to do, Markov chain, and we crossed our fingers and hoped it would work out. So I guess the way to say this is the biblical saying, seek and ye shall find. That's going to be true here if you don't seek too much and you look in the right places. So we formulated this problem, and now what we're going to do is we're going to find that we're going to stare at this. This is the key idea, and this is an idea that's both simple and subtle, and very smart people didn't know this idea. Like Milton Friedman, as smart as he was, didn't know this idea. He encountered a problem which, if he had known this idea, could have cracked it. He thought it was one of the best problems he ever encountered in his life. Didn't solve it, gave it to somebody else who did solve it, but to solve it, the person had to invent dynamic programming. It's a deceptively subtle but powerful idea. We're going to write down an optimum of what's called a Bellman equation. And I'll just write it down. And it's a version of what we wrote down before. So the idea is today, this is today, and this is the optimum value. This is the value of the problem starting from state X today, where X is this ordinary state. So the state now has a pair. There's a state X, which is that part, but there's also the Markov part. So that's the Markov state, and that's our ordinary state. When I say the ordinary state, that's just the junk that's right in here that we had before. And we'll see an example of what that is. So this says that we're making this guess that our value function is this quadratic form, but now the matrix P and this constant rho depends on I. So turns out this thing satisfies the following equation, which is a generalization of the equation, the Bellman equation we had from last time. And what it is, so here's the deal. Today, that's today's penalty, our loss today. And we have to know what's our loss tomorrow. Of course, it's good to have my scribble thing because I have to add a plus. There's a plus. I left that out. Plus beta, that's my discount factor. Now, tomorrow, I don't know a whole bunch of things about where I'm going to be. I don't know what this shock is, W. So I don't know what that is. So what I do there is I take an expectation over it. But the expectation is going to be conditional on where I am today. Now, where I am today is, that's in state I. Well, where I am today is state X and state I. Now, the transition law, there's a transition law, and I know what that is. But I don't know where I'm going to be tomorrow because I'm going to be a state J tomorrow. So my value function I want to weight it tomorrow is a J. But I just write this down and I get, if I stare at this, there's an I on this, there's an I here, and there's here, what is here? There's P1 all the way through Pn. And there are my Markov chain pi is right in there. So if I work with this, I can get the following And this is just linear algebra. I'm not going to ask you to do it, but you could do it. You do it faster than I am because they're just formulas for maximizing or minimizing quadratic forms. There's linear algebra form for doing matrix minimization. So you get these equations. You get pi here. You get all this junk on the right hand side. There's my matrices. I'm summing over. That's tomorrow. Remember, I is today. I have to use my dyslexia little device. J is tomorrow. So I'm summing tomorrow. I don't know where I'm going to be tomorrow, but I know the probabilities. So I just sum that, and there's my PJs, PJs, PJs. And if I just stare at these equations, these are people call them coupled Riccati equations. And the punchline is they're very easy to solve. And it's very, the descendant, the daughter or son of the homework from last time is, maybe you'll see one of these is, I give you one of these god-awful problems, and then your job is to tell George and me what equations to solve in order to give you the optimum decision rules. So here we go. Here's our equations for p's. Then we get the rows. Once we have the p's, we can get the rows from this. There's my j, simple formula. And you'll notice in my optimum decision rule, before I had the decision rule f that was the same for all time. Well, here, it's not the decision rule isn't the same for all time. It's the same whenever I'm in Markov state I. So there's a different decision rule, F1, F2, Fn, for each of the Markov states. That's it. So now, I guess every father or mother thinks his baby is really beautiful. But even though his or her friends won't tell him, lots of times the friends won't. So beauty, they won't say that they don't agree. So beauty is in the eye of the beholder. And I'll unmess this. But to me, with or without these red marks, these are beautiful equations, because something that looked very complicated, and maybe at first sight, it's just a generalization, a pretty simple generalization of what we had earlier. And the punchline is these are easy to solve. Just a digression. Way you solve it, I'll tell you how to solve it. I'm going to get really ambitious here. This is likely to be a disaster. So this is going to be an attempt to be very fancy. Okay, here's the way you solve this. You just take the right-hand side of this equation and you make a guess at the PJs. Just make a guess. So make a guess at the PJs. Make a guess. Now, if you knew all the PJs, you'll notice there's only PJs here. Make a guess. There's these sums. You know everything on the right-hand side. You make a guess at those. If you made a guess at that, how many equations is this? How many equations is this? There's an equation for I equals 1, 2, all the way through n. So if you guess at the PJs for j equals, this is kind of a digression on a computer programming class. You guess at these. Well, these are just n big ugly equations, but they're just matrix equations. What do? You know how to multiply matrices, you know how to transpose them, you know how to invert them. You just do that. And you get a new set of guesses for a new set of matrices here. Now take that guess and substitute it in over here and do it again and just iterate. So the way you do it is, this is called iterating. We're just going to iterate to convergence. And if you ask George and me to solve these equations, that's what we're going to do. And there's theorems that say that's guaranteed to work. Works like a charm. So even though these are fancy, they look like equations, they're very easy to solve on a computer. Nobody can solve them by hand. Okay. Okay, good. So now I'm going to go back to my, again, this is likely to be a disaster. There you go. I'm back in red. Okay. So now I'm going to show you some models inspired by Robert Barro. When I say inspired by, taking a little bit of liberty. So here's what we're going to do. I'm going to let TT be total tax collections. Beta is a discount factor. Okay. And I'm taking this notation from Barrow. I apologize for this, but I'm going to use some different notation later in the class, which I'm going to take from George Hall and me. But I'm taking this from Barrow in case you actually go read those papers sometime, which you'll be able to read really easily now, because we do stuff Barrow doesn't do. Barrow doesn't actually solve his model. And it actually says a few things about his model which probably aren't going to hold true once you actually solve them on a computer. But what we're going to let is, we're going to set H equal to 2. That's our horizon. And the government's going to issue short and long-term debt. So in Barrow's notation, BT T plus 1 are time T plus 1 goods that the government promises to pay at time T. And BT T plus 2, those are time T plus 2 goods that the government promises to pay at time T. So at time T, what's the government choosing? It's choosing a BT T plus 1. I'll pay you that tomorrow, and I'll pay you that 2 periods from now. And you could say we got lazy because we could have gone all the way out to BT T plus H, but we just didn't do it. You'll see it'll be easy to take our apparatus and do it. Okay. GT are government purchases. Okay, what are PTT plus 1? Those are Hicks arrow prices. Okay, and what it is, it's the number of time T goods received per unit of time T plus 1 goods promised. And PTT plus 2, that's the number of time T goods received per time T plus 2 goods promised. So these are just arrow Hicks prices. Okay? And this is the way Barrow writes this. Okay, and here's a comment. These arrow Hicks prices are inversely related to appropriate gross interest rates on government debts, the inverses of gross interest rates on government debt. Okay, and the stochastic process of government expenditures is exogenous. This isn't a model about choosing government expenditure processes. It's a model about how do we finance them given that we have to. Okay. So now here's the deal. We're going to make PT T plus 1 PT T plus 2. Those are going to be functions. What are they? We're going to make those functions of the Markov state. So, and there's going to be a transition stochastic matrix. So we are now going to make interest rates or arrow Hicks prices vary over time. And in particular, there's going to be a Markov state, which is going to go I equals 1 through n, and n could be very big. So there are going to be periods of high and low interest rates. There can be periods of twisting term structure of interest rates. That's all going to be captured by just making these things functions of the Markov state. That's what we're going to do. That's where we're going. Okay, so we're going to have initial conditions. So at time 0, you're going to come in owing some debt. This is the debt you owe. There's going to be a state Z0, and there's going to be an initial Markov state. I'll show you what this is. So what's the government going to choose now? Now the government's going to choose in this Barro model. It's going to choose a whole financing strategy. It's going to choose taxes. It's going to choose short-term debt and longer-term debt to issue. And what's it going to maximize? Well, Barro wouldn't have, actually, if you read his paper, he doesn't have these things in here. He doesn't have these things in here. He gets those out. So I'll put these things not in Barro. But if he actually tries to solve it on a computer, he's going to leave them in there for reasons I'll tell you. So Barro's just going to have R of TT, and he's just going to square it. So in particular, he has this function, but so Barro doesn't have these two terms, but I'm going to put them in. And they're kind of smoothing terms. They're additional smoothing terms, which we're going to need to control something that's well known to, you've all heard of portfolio theory. And there's kind of you could call it a scandal or a curious feature of portfolio theory, in that it gives very extreme advice. So the so-called quantitative portfolio theory that comes from Markowitz, that's used, it's the foundation of optimal portfolio theory. It gives very extreme advice. I'll tell you about that. It gives portfolios which are very extreme. They're very large positive holdings and very large negative holdings, big longs and shorts. And that theory tells you to do that. It's going to tell us to do that. Our government, see, is solving a portfolio problem. It's choosing how much to issue long and short. And this problem, I'm actually letting it go long and short. It can borrow and lend. And depending on what these arrows, what this little dynamic programming problem is really, it's smarter than we are. Depending on what we put in for these exogenous interest rates, this government is going to realize that it can play the yield curve. It can arbitrage the yield curve, and it's going to want to. And essentially, these terms are there to attenuate that. And I'll just tell you, this is a problem that's endemic to portfolio theory. And I'll just tell you, there's something called the Black-Litterman model by two famous great economists. I was actually this guy's thesis advisor, a little bragging. They worked at Goldman Sachs, and they invented a model to attenuate portfolios. It's a famous model that people use to address this problem. We're using a little different approach, but it's actually, in some ways, it's similar to the Black-Litterman model. So I'm willing to talk about that in a digression sometime, but okay. We kind of backed into it because, my job isn't to teach you finance and portfolio theory, but my job is to teach you fiscal history and fiscal. So how do I back into this? I want to teach you fiscal history, and then the governments that we're talking about since the beginning of the American Republic and before, trying to figure out how should they finance government expenditures, and should they borrow, and if they borrow, in what form? But governments simultaneously borrow and lend. So what should they do? The United States government borrows and lends. You realize that it has big government debt, but it has big asset holdings, huge holdings of student loans, other kinds of loans to people. So this is a real practical problem. Okay, so anyway, good. So there's the objective function, quite simple. forgive me, but when I seen this problem, it's quite exciting in terms of both its technical features and how it maps into practical problems, both in history and today. So now here's the constraint. The maximization is subject to these constraints. Okay, so there's going to be a couple of set of constraints. These are called the endogenous state variables. And here's the deal. This is the state. This is the endogenous state component of the state, which I'll call xt. And this is just bookkeeping. So this is the control. So today, notice today the government is choosing how much to issue in 1 period Arrow securities, 2 period Arrow Hicks securities. And then the state is, well, today it owes, today what is it, what's falling due? Well, a couple things. It's got what it has to keep track of. This is how much it borrowed in 1 period securities yesterday. That's what this is. This is how much it borrowed in 2 period securities yesterday, and they're falling due today. You got to pay them. But it also has to keep track of this. This is what it issued yesterday. It's going to fall due tomorrow. It's going to have to keep track of that. So if you look at these matrices doing, so this is just one of our, this is a little A matrix, that's a little B matrix. Okay. And then here's my government budget constraint. Or actually, I've added something. My total tax collections have to equal GT. And then, okay, this is what's due today. And DT, if there's no default, DT is just 1. DT equals 1 if there's no default. But what I'm going to do, just to be fancy, because it's easy for me to do, I'm going to make DT, it's a function of a Markov state. So there's going to be just some exogenous states where, through an act of God or nature, I'm not going to pay. And I have the opportunity not to pay. It's going to be debt forgiveness. And that happens from time to time. The basic Barro model, Barro had DT equals 1, so this wasn't in there. This was just 1, and this was 1. But this model can incorporate defaults of a certain kind. And then, what is this? Well, that's what I'm choosing to promise 2 periods from now. That's what I'm promising to promise 1 period from now. And here are my Arrow securities prices, my Arrow Hicks prices. But I'm going to make these things, so I'm going to make all of these things be driven by a Markov state, a finite state Markov chain. That's what I'm going to do. And then what am I going to do is, this part is just what we had last week. Government expenditures are going to be exogenous, and they're just going to be driven by this Z process. And I'm going to use this. And I think later I'll do some, not today. I'd hope to, but I didn't get to my calculations. I'm going to, I'll show you some stochastic processes. This can capture either temporary or permanent government expenditures in a really nice way. And now what am I going to do? I'm going to have my defaults, my Arrow security prices, and now, so why not be fancy? I'm going to have my, look at this. I'm going to have my stochastic process for government expenditures. Now I have matrices. See, there's a matrix UGT. And these matrices, I'm going to make them functions of time. Well, what kind of functions of time? They're going to be all driven by functions of this Markov state with this transition. That's it. So I've got a lot going on. So what's going on here? I've got a term structure of debt now, not just 1 period debt. I have interest rates that are no longer constant. They're not just 1 period interest rates, they're 1 period, 2 period, and I could go on out. They're moving over time, but they're just functions of this Markov state I, which I'm controlling and governing with this matrix pi. That's how I'm using to describe it. that's it. Now it's just bookkeeping. This model is going to be, I'll show you how to do it. Model is going to be a Markov jump unit quadratic dynamic programming problem. I'll just remind you of a very special case. So you'll see this is a generalization of Barrows' model. I already anticipated this. What did Barro said? He said his loss function was a quadratic function of taxes. He didn't actually do this, but technically he had to do it. Plus epsilon, where epsilon's a little small number, times the stock of debt. He actually has to do that. And that's needed to present a Ponzi scheme. If you don't have this number, the dynamic programming problem will tell you just to borrow increasing amounts forever, and there'll be no penalty to doing it. The Bellman equation, the Riccati equation will discover that. It's very smart. So to rule that out, we have to put this penalty in. That's a technical thing. So then we set the default to 0. Barro just assumed, remember Barro assumed that Barro security price was equal to beta. He didn't have 2-period borrowing. So that's it. So I'm going to hand out these notes which I wrote up, but which is just preaching. It's telling you a little bit about why I'm adding this term and why I'm adding this term, and it's to prevent the government from doing really wild things with government debt, which it will want to do. It will want a so-called arbitrage. It will use fiscal hedging. It will activate the government as a portfolio manager, where it's going long and short in a big way. Okay, so that describes forces that are really there that are really present, and you will actually see, like famous economists like Alan Blinder made a proposal at the beginning of the first Clinton administration, Bill Clinton's administration, that the government he was an advisor to President Clinton, the first President Clinton, likely to be an advisor to the second President Clinton, depending on what happens 3 weeks from yesterday. He advised that the government play the yield curve, that it do a long short play. So I've explained this already, what DT is. Okay, so look what we can do just by being a little creative. This is the fun part. We can display instances of this Markov chain and functions of the Markov chain that capture rollover risk. See, it could be that sometimes PT t plus 1, PT t plus 2, they're both equal 0 for some states. They're both equal 0. That means how much do you get by promising to pay in the future? Nothing. You have no opportunities to borrow today. So that could happen. And if that happens, the calculations will handle it. It'll say, boy, you got a tax today. So the consequence of rollover risk of certain kinds is it impinges immediately on your tax policy. That, by the way, is at the heart of various models of sovereign debt. Okay. There's a little section here I think I'm going to ask you to skip, but question is, how would you calibrate, if we're actually going to set up this model, how would you choose these things as functions in the Markov state? And we can use a little bit of advanced finance to do that, in terms of calibrating these things to capture some realistic interest rate movements And there's a literature on something called stochastic discount factors. It's a general theory and empirical analysis of interest rates. We know a lot about that, and by using that, we could calibrate, and that's what we do. Okay.
Sorry, Tom, we dropped out for a moment. I'm not sure what happened.
Oh, can you hear me now?
Yeah, I can hear you now. Yeah.
How long did you drop out?
30 seconds, maybe?
Okay.
Yeah, very short amount of time.
Okay, that's actually good because I was talking about something I shouldn't talk about. I was talking about calibrating the interest rate process.
Okay.
Okay. And there's a little section on exogenous defaults. I don't know. I don't want to insult anybody from Argentina or Greece or anybody, but there's haircuts. These Ds could be haircuts that the government occasionally encounters. So now, the reason that's an interesting remark is what this means is we have a model for describing how this would be a German view. It would be a German view of Greece. If I change the stochastic process for D in terms of how forgiving I am in haircuts, that's going to affect what Greece chooses for TT, BTT plus 1, and so on. It's going to include that. And that's a point that the Germans make, that if you're in a process where, if you set up a regime where a country can expect these occasional haircuts, that's going to affect their behavior and what their level of debt is. So this model will capture that. Okay, so then this is bookkeeping. This just shows. So this is what we want. Seek and ye shall find. And this down here is find. What it shows is how to create matrices that map this into a Markov jump linear quadratic dynamic programming problem. So all this does is it creates the matrices, and it shows how the matrices, this is all bookkeeping. I'm not going to ask you to, actually, I'll ask you to look at this if you challenge me and say this, I haven't shown how this could be done. It is actually done. It just shows how to put these this structure into a Markov jump linear quadratic programming problem. Okay, I want to spend my last few minutes, I know I pounded you a lot, just by circling back, and I'm going to show you another model. So this model is going to, it's going to be, this is going to be more in the Hall-Sargent notation. I'm going to change notation and more like on my Hicks arrow notation, very close to what we've used in the previous homework, in the homework 1 actually. So here's the idea. I'm going to write the government budget constraint now like this. This is how we wrote it in several lectures. What ST plus J is, that's today, and that's how many goods the government promises to deliver T plus J periods from now. And I'm now writing my arrow Hicks prices like that. T is the superscript is today, the subscript is tomorrow, the day after tomorrow, and so on. So this is my government budget constraint. Now, the way I've written it is, look at this. Yesterday, that's yesterday, the government promised to deliver all of these things. Today, so it delivered this. It has to pay this yesterday. I'm sorry, to promise this yesterday, it has to pay this today. If you look at these sums carefully, well, it's not going to have to pay this today, but it's made promises from tomorrow on, and those get revalued because those are today's price. These are today's prices. Yeah, here's the way to write this. This is today's prices. And that is yesterday's promises. So yesterday's promise got revalued because those prices got changed. And I'm going to make them change. They're going to be functions of this Markov state. They're going to bounce around. And what is this on this side? This is today's promises. So what I'm actually doing, I'm actually buying and selling and reissuing promises for tomorrow, and these are today's prices. And this is how we wrote the government budget constraint before. And again, G is what it was before, T is what it was before. Okay, so now things are going to get really pretty in this framework, because now I'm going to have, you remember, finding the state is an art. That's what dynamic programming is so valuable, because what it does is it's a tool that liberates your creativity. It constrains and liberates your creativity, because it says, okay, you have this powerful tool. It's up to you to find a convenient state vector and control that makes the problem tractable and illuminating. So here's going to be the state. It's natural. It's what you promised yesterday. It's this whole, and what did you promise yesterday? You promised a whole, yeah, so that's yesterday. So you can't do anything about this today. Those are the promises you made. And what did you promise? You promised a whole vector of payments today, the day after tomorrow, and so on. So those promises are outstanding. And then what is this? What can you do today? Well, today you can make a whole new vector of promises. So this is what you promised to pay as of last time. You're coming into the period with these promises. You're going out with these promises. And I'm calling those control. And I'm making this control vector very big. It's as big as H. And that I'm allowing you to reschedule everything every day. Every period you can reschedule. Remember, my interpretation of the Barro model was that you were much more limited. But allowing you to reschedule in this flexibility actually makes the description of a model quite simple. Okay, so now I'm going to define this augmented state variable as this X augmented with the Z, which is going to drive the G process as before. And now I use my trick. This is going to be a function of the Markov jump. And then now everything's bookkeeping. Everything's bookkeeping. So I can just define matrices. And this will now fit into my Markov jump linear quadratic programming problem. And you know, again, this is a lot of bookkeeping, accounting, you could think, using linear algebra. But all I'm doing is forming matrices such that, so at the end of the day, you'll see, if you look at this, here's kind of a key thing. I end up writing taxes because my objective function is going to involve taxes squared. My objective function is going to be, my tax is just going to be, it's a function of this X, where that's some matrix. It's a function of that Markov jump thing, but that's just going to depend on I. Inner product with this, that's fine. That's just going to lead to a matrix that's indexed by I. This is easy. Again, that's a function of the Markov. And this, what is this PT thing? That PT thing is that whole vector. PT is the whole vector of Arrow Hicks prices, and they're bouncing around. So what we've done is we've created, a pair of models in the spirit of Barro. I'll just make the comment that to make this model well behaved, to prevent the government from doing very big, long, and short things that seem completely inconsistent with the data, this model is going to require that we impose some quadratic costs on making those big things. And the logic of the model tells you this. Without those costs, the government's going to do some really outlandish things. Like it might have really huge long positions and really huge negative positions, longing and shorting things. That would be many times the world GDP for a little country. So if the program tells the government it wants to do that, and you kind of ask interior to the model, why doesn't the government do that? You have to say either we have the objective function wrong, so there's some cost that we omitted, or that's what we're going to do. Or you could say, well, wait a minute, you've assumed a certain structure of prices and expectations about how the government thinks prices are going to move. And when we adopted that these prices were a function of a Markov state, and that Markov state was governed by a transition matrix pi, it's exactly at that point that Black and Litterman said, well, we're going to deviate from rational expectations, and we're going to impose different views than those, and we're going to say it's the reason the government or the portfolio manager doesn't do that is because he doesn't share those views. He has views which make him much more cautious. That's the Black-Litterman line. You're going to have to do one of those two things because portfolio theory drives you into this this conundrum. So that's just the way things are. Portfolio theory and economic theory in general is not good, or is challenged. Let's say is challenged in terms of actually explaining why people pick the portfolios that they do. This is kind of widely known, but it's not widely talked about. It's a little bit of an embarrassment. Okay, I think that's where we're going to end tonight. And so next time we're going to be heavier on the history than on this, but these issues that we're talking about are going to reappear throughout the histories that we're going to talk about.